يكون نويزي زي الخشخش كذا. اوكي، هذا حيصير تلاقي الصوت زي كذا، يعني نويز مثل كذا ادد على السيجنال. بينما اذا كان في نويز بسيط، خلينا نقول السيجنال تو نويز ريشيو is higher than this، يعني it's not very low، ساعتها حتلاقي نويز خفيف، الصوت فيه نويز لكن نويز خفيف، مثل ما تفتح إذاعة AM وتكون مثلا الإذاعة هذه جاية من مكان بعيد، تلاقي الصوت نويزي، أو بعدين تقرب تلاقي الصوت أحسن، بعدين تقرب. مثلا لما تسافر الرياض تحس بالشيء هذا، لما تفتح الإذاعات اللي تبث من الدمام وأنت ماشي في طريق الرياض، بعد مثلا 100 كيلو 150 كيلو تبدأ تحس بالنويز. كل ما تزيد أكثر الديستنس تحس إنه نويزي أكثر. أبغاكم تسوي الشيء هذا. وبعدين signal to noise ratio لما تكون مرة عالية، اللي هو النويز باور is extremely low. تمام. فهذا اللي هو part 2. part 1 اللي هو basically generation of the audio signal and so on. part 3 is similar to part 2 لكن بدل ما يكون في added noise، okay, we'd like you to do low pass filtering with using different cutoff frequencies. خلينا نقول أول فايل، خلينا نقول إنه الفايل الأول كان الباندويث حقه 4 كيلو هرتز مثلا أو 5 كيلو هرتز. أبغاكم تسوي فلتر 3 فلترز، فلتر with a cutoff frequency أقل من المينيمم من الباندويث حق السيجنال، خلينا نقول 2 كيلو هرتز. أبغاكم تشوفوا كيف الصوت يتغير، اسمعوه شوفوا كيف يتغير، مو بس تسمعوه، تشيكوا حتى على الباور سبيكتر دنسيتي حقته كيف صارت. ونفس الشيء لما يكون الباندويث معقول، مثلا 4 كيلو هرتز، أوكي 4 كيلو هرتز أو أقل شوية أو حولها. بعدين لما يكون أعلى من كذا، يعني لما يكون مرة قليل، مثلا إذا هو الباندويث حق السيجنال في الكاتوف في الباور سبيكتر دنسيتي خلينا نقول إنه هو 5 كيلو هرتز، أبغاكم تسووا فلتر 2 كيلو هرتز، واحد 4 كيلو هرتز مثلا، أقل من الباندويث المطلوب بشوية، أقل من الباندويث المطلوب بكثير، وأعلى من الباندويث المطلوب. نفس الشيء في الهاير فريكونسي الأذر فايل، اللي هو الفايل اللي فيه مثلا 20 كيلو هرتز ولا 15 كيلو هرتز. أبغاكم تسووا فلتر with 5 كيلو هرتز، one with 10، one with the required bandwidth، وتشوفوا كيف الصوت كل مرة يتغير. ونفس الشيء الباور سبيكتر دنسيتي. فهذا تقريبا هو البروجكت. اوكي. فانتوا عندكم في الريبورت، بس خلينا لو في الريبورت عندكم التو فايلز، طبعا لازم يكون في ويل ريتن ريبورت كومبليت ريبورت مع كل الريزلتس والفيجرز اللي طلبناها فوق. وطبعا الفيجرز مو بس فيجرز، يو نيد تو ديسكاس الفيجرز، تتكلم تعطي كومنتس عليها، ايش معناها، ايش هذه، ايش معناها هذه. والتو original audio signals using some well-known extensions بحيث أن تكون سهل علي أن أشيك عليها. وعندك في البارت الأول 6 noisy signal files، 3 for each audio signal، كل واحدة الأوديو سيجنال الأولى والثانية كل واحدة I need 3 noisy signals، واحدة very noisy، واحدة moderately noisy، واحدة with low noise. ونفس الشيء filtered signals for every audio signal I need 3 low pass filters، واحدة with very small low pass filter bandwidth، والثانية with moderately small، والثالثة with enough bandwidth. طبعا غير الفيجرز اللي داخل الريبورت. تقريبا هذا هو البروجكت. تفضل.
ايوه زاد فضلك دكتور. معناه يعني حسب اللي فهمته منك، بس في البارت الاول راح نسوي الجنريشن. هل الجنريشن محصور انه لازم نجيب ملف من برا او ممكن نسجل الملف من الماتلاب؟
ما عندي مشكلة. It's either way.
طيب
as long
طيب.
as long as it two files have two different frequency components، واحد with large bandwidth واضح جدا، والثاني with small bandwidth. عادة السمول باندويث اللي هو talks of people، صوت الناس بالذات الرجال، يعني الباندويث حقنا احنا منخفض. الحريم يمكن لأن الصوت نحيف أو الأولاد صوتهم نحيف تلاقي الفريكونسي كومبوننتس أعلى، لكن بصفة عامة أصوات الناس الباندويث حقها منخفض مقارنة بالأشياء الثانية. تفضل.
طيب والبارت 2 راح
بس عفوا، البارت الأول includes you need to check the statistical properties of every signal، اللي هي الافريج، الافريج باور، الفاريانس، الماتلاب، سوري البي دي اف using الهيستوجرام، الاوتو كورليشن فانكشن، الباور سبكترال دنسيتي، هذا كله في الجزء الاول.
ايوه طبعا بس انا اقصد انا على الجنريشن
شو
يعني طيب في البارت 2 اللي هو راح ندخل النويز من الماتلاب نفسه باستخدام الاي دبليو جي ان اتوقع، صح ولا؟
باستخدام الراند ان، انا معطيكم الفانكشن هنا.
ايوه الراندن راح ندخل، يعني راح نستخدم الملف الاول اللي هو صوت الهيومن، وندخل عليه التشويش هذا النويز من الماتلاب نفسه.
ايوه
كلام
يعني انت
صحيح؟
لازم تشيك كم الفيكتور حق الصوت، الفايل حقك كم sample, and you need to generate a random noise vector with the same number of samples and you add to it. لكن بحيث ان السيجنال تو نويز ريشيو مثل ما حسبت لكم اياه هنا. average
ايوه
signal power divided by gamma, where gamma is the average signal power found in yeah. Okay.
الاس ان ار لازم نجيبها من يدويا، يعني ما نقدر من الماتلاب، صحيح؟
لا لانه شوف، هو الراند ان انت ممكن تسوي generation with zero mean, zero, and any variance 1 مثلا. الآن what is the variance of your Gaussian noise؟ الفارينس اللي هو جاما، هذا اللي في المقام، should reflect your signal to noise ratio. إذا أنت قلت لي السيجنال تو نويز ريشيو 10 دي بيز، تحول ال 10 دي بي إلى linear scale اللي هو 10 to the power SNR divided by 10. الآن هذه أعطتك value مثلا 10 ولا 5 linear scale. 5 equal the average power signal power اللي حسبتها أنت في part 1 divide by gamma. هذه gamma هو الفارينس حق الراند ان، فأنت تحسب الجاما من هذه. ولا otherwise كيف حيتغير؟ كيف حيكون عندك different signal to noise ratios؟ الراند ان الفارينس حقها هو الباور اوف ذا نويز اللي هو الجاما. واضحة؟
الفاريانس حق الراندن راح يكون هو الباور
حق النويز،
حق النويز.
لأنه أنت عندك زيرو مين، فالفارينس equal expected value of x squared، صح؟ أو n squared.
ايوه
فهو الفارينس، فالفارينس reflects the power of the noise.
تمام، ان شاء الله انه اجاتت ان شاء الله.
تمام شباب، أي سؤال ثاني؟
يعطيك العافيه دكتور.
حياك الله. It should not take that long by the way، بالذات إذا جروب 4 طلاب مثل ما قلنا. It should be صراحة شغل 2-3 بالراحة، إذا توزع الشغل بطريقة يعني مناسبة. Should not take that long. بس أنا I hope إنكم you get excited about it، يعني شيء practical. ما حبيت أعطيكم شيء theoretical تجلسوا يعني ما تستمتعوا فيه. هذا المفروض إنكم يعني you should play with it. أوكي.
دكتور بس نقطة واحدة، البارت 1 بي you can use histogram from MATLAB. ايش تعني بذا؟
يعني أنا قصدت التالي، هي ظهر فيها misunderstanding في الجملة هذه. أنا أبغاكم for the average والaverage power والvariance تبنوا your own functions. ما أبغاكم تستخدموا أي شيء في الماتلاب. أنتوا احسبوا الافريج والافريج باور والفارينس your own functions. بينما في البي دي اف والاوتو كورليشن فانكشن والباور سبكترال دنسيتي you can use مثلا هيستوجرام في البي دي اف and so on. use ready functions. هذا اللي قصدته. اوكي. فمثلا البي دي اف الهيستوجرام should give you a function an output that looks like similar to the PDF زي ما تكلمنا في الكلاس هنا.
شكرا
واضحة؟
دكتور.
حياكم الله. أي سؤال ثاني يا شباب؟ واضح؟ ما في؟ طيب والديدلاين باقي لكم تقريبا 10 أيام 11 يوم، يعني try to manage your time well and submit it. Okay, so now let's switch gears to the material. طيب, so last time we discussed the, autocorrelation function and its relationship to the power spectral density, and we established the fact that the power spectral density is sorry, the Fourier transform of the autocorrelation function, and the autocorrelation function is the inverse Fourier transform of the power spectral density. This is for wide sense stationary. For non-wide sense stationary, the power spectral density is the Fourier transform of the time average of the autocorrelation function. So the autocorrelation function will be time changing, time varying function. Then the power spectral density will be the Fourier transform of the time average of that autocorrelation function. And we give several examples and try to explain the meaning, the physical meaning of when the power spectral density is wide. Sorry, the autocorrelation function when it is wide, what happens to the power spectral density? It becomes narrow, which means that it has small bandwidth. It contains small amount of frequency, high frequencies. بينما when the signatures with the autocorrelation function varies fast, which is a narrow autocorrelation function, then you end up with a wide power spectral density, which means that the bandwidth is large. And we try to explain the relationship between the rate of change and the frequency in that context. And then we discussed the properties of the power spectral density, and we said in order to check whether it's a valid power spectral density or not, you need simply to check 3 properties, whether it's a positive function, even, and real. And we continued with examples. In this example, we talked about some signal that has low pass and band pass components. And then we talked about the white noise, and we said that it's noise because it's a random process, so it's not deterministic signal, and it's white because it contains all frequency components, as the white color contains all the colors. And we say that it's unrealizable because it contains an average power of infinity, which is impossible. However, if you look at real noise that is generated through resistors and other electronic components, you will find that it's not really a flat PSD, power spectral density. It's a power spectral density that is maximum at 0, and then it decays slowly. However, this slowly means that even it reaches 0.9, which is 90% of its maximum, even at very high frequency of 1000 gigahertz. So it's an extremely wideband noise that looks like white noise for any system of operation that we work within, whether it's a 5G, 4G, 3G, whatever. Usually our bandwidth is within 5 megahertz or so, 20 megahertz, not more. So within any bandwidth of operation that we are interested in physical systems, most of the time, or always, you will find that the noise looks like a white noise. واختتمنا الكلاس with the band limited low pass white noise. When we low pass filter a white noise, we end up with a power spectral density that looks like rectangular up to from minus W to W, where W is the bandwidth of the low pass filter. And when you look at the power spectral density, it looks like a sink. And we explained that we contrasted 2 cases when you have a large bandwidth and a small bandwidth. Large bandwidth means that many frequencies have passed, which gives you an autocorrelation function that is narrow, which means that the noise is a fast changing or fast time varying signal, compared to a small bandwidth where many frequencies have been depressed and only very low frequencies were passed. And you can see that the autocorrelation function would be wide, which means that you have a noise or a signal that is slowly changing. And we stopped here. So today what we'll do is we'll look at the bandpass, band limited white noise, and then we'll start chapter 8. أي سؤال يا شباب so far؟ Okay, so band or bandpass band limited noise is a noise that is, or a white noise that is bandpass filtered. Bandpass filtered معناها ايش؟ معناها you filter it at certain frequency، هذا نسميه center frequency of the filter، وهذا الباندويث of the filter. So we have a bandwidth of the filter equals W, with center frequency of the filter equals omega 0. Okay? Similar, you can see that the image, because it's a real filter, you can see that its image in the negative frequency is the same. So it's an even function as usual. So, and in mathematics format, it looks like this. It's some constant for omega, absolute value of omega between omega minus W over 2 up to omega 0 plus W over 2, where W is the bandwidth. And if you take the inverse Fourier transform of this, you end up with the autocorrelation function that looks like a sinc. So this is equal P sinc W tau over 2 multiplied by cosine omega 0 t tau. So it's basically a cosine wave, however that is multiplied by a sinc. So the cosine wave decays هذا envelope. This is the envelope. سميه envelope of the cosine omega 0 tau. هذا الانفلوب اللي هو dashed curve, where basically it shows that how does the amplitude of the cosine changes over tau. لو تلاحظوا انه so this is the cosine omega 0 tau، وهذا الانفلوب of it. envelope اللي هو عبارة عن sinc function. تمام يا شباب؟ So this is how the autocorrelation function looks like.
دكتور
تفضل.
why we take a band pass or low pass for the white noise when at the end we are going to get like a constant?
What do you mean like a constant?
Because it is decaying very slowly over a very large bandwidth.
هذا التايم، هذا التاو قصدك، ولا
لا
تتكلم
دكتور.
على الباور سبيكتر دنسيتي؟
أنا أتكلم عن الوايت نويز دكتور، إحنا ناخذ باند باس ولو باس.
ايه اوكي ثانك يو. طيب احنا why are we talking about low pass و band pass? Because at the end, excellent question. At the end خلينا نقول اي سيجنال، انت الان عندك سيجنال، انت ارسلت m of t ولا خلينا نقول x of t، تمام؟ This is your signal of interest. انت ارسلتها. What do you receive at the receiver? You receive y of t plus n of t. Now this is a white noise. Now in any signal عادة band limited مثل الفويس اللي جالسين تشتغلوا عليه في البروجكت مثلا low pass filter. You want your own signal. So in order to receive this you need to low pass filter it. Then أو band pass filter it. إذا أنت ترسل signals على high frequencies. ما أدري أنت أخذت 370 ولا لا؟
I'm taking it right now.
Yeah. ف 370 أنت أخذت مثلا ال heterodyne receiver where you send many signals using some time division multiplexing over certain carrier, and in order to receive it, or using frequency division multiplexing, and in order to receive every signal you need to receive it using some band pass filter according to the center frequency of every signal. واضح؟ فالسيجنال نمبر 1 حيكون السنتر فريكونسي حقها اوميجا 1، سيجنال نمبر 2 جنبها بتكون، سيجنال نمبر 3 جنبها and so on. Okay? So you need to filter your signal. You need, in order to receive a specific signal x of t, you need to filter it at the إذا هي low pass filter you need to filter it low pass filter. إذا هي band pass إذا هي using frequency division multiplexing you need to filter it using some band pass filter. في كلتا الحالتين you are filtering a noise component in addition to your signal. فعشان تفهم كيف the received signal looks like in the time or the spectral domain, you need to understand how does the noise look like after the filter. واضح؟
Yes.
عشان كده جالسين نتكلم عن الباند باس الباند ليميتد اللي هو اللو باس فلتر white noise والباند باس filtered white noise, because in practice my signal I will have a noise added on top of it غصب عني زي ما تكلمنا, because electronics add noise. So in order to understand my received signal اللي هي أنا الآن بستقبلها في الموبايل فون ولا في الجوال ولا في اللابتوب ولا في الإذاعة ولا whatever, I need to understand how does the noise pass the filter and how does it look like after the filter. تمام يا شباب؟ Okay, so basically this is the way the bandpass filtered white noise look like. أي سؤال؟ طيب, let's have a practice. Now we have a wide sensitivity random process, or noise process that has an autocorrelation function given by this. It's an exponential function. لما ترسمه يعطيك هذا الفانكشن. Okay, find and sketch the PSD. طبعا the PSD, in order to get it, you need to apply Fourier transform, and we have this relationship here. Okay, so the power spectral density looks like this: 6p over 9 plus omega squared, which looks like this. Now, assuming that my function was بدل 3 حطيت لكم a. So instead of that خلينا نقول r in n of tau equals p e to minus a tau. So if you have large a ايش يصير؟ If you have large a يا شباب كيف شكل ال autocorrelation function؟
Narrower will be narrower.
نورو إيه الباند
exactly.
بقل.
ممتاز. لا اكتب ايش جالس تقول؟ larger a means narrower autocorrelation function. So what happens to the bandwidth يا شباب؟ Take the Fourier transform of this.
Increase.
Will expand.
Will have a bandwidth that looks like so basically the bandwidth is large. والpower spectral density is wide مثل ما تكلمنا ذيك المرة. تمام؟ بينما if you have a small a means you have an autocorrelation function that is slowly decaying, which means you have a slow, this is fast signal. This will be slow signal, slow moving signal. تمام؟ Small a. Now if you take the Fourier transform of this, what do you get? ايش رايكم؟ وايدة ولا narrower?
Narrower.
نورو
Exactly. So the bandwidth is small. ونفس الشيء ال PSD is narrow. تمام؟ You need to connect these things together so that you understand the effect of لما تكون السيجنال تتغير بسرعة معناها it has high frequency components, because rate of change means frequency. Higher rate of change means higher frequency component. طبعا المفروض انكم دارسين الاشياء هذه في ال 207 و 370, لكن هنا we are trying to put it in the randomness context only. لكن ال rate of change وعلاقتها بالفريكونسي I assume that everybody of you have taken it somehow في ال 207 و 370. صح؟ صح يا شباب ولا لا؟
اخذناها 370.
ممتاز. So you have
And
it passed by you sometime. Good. Okay, so This is basically it for chapter 7. An annotated version is already uploaded to your OneNote. Any questions as well? Before we move to chapter 8, which is the last chapter. No question? You have it already in your content library. Okay, chapter 8. What is it about? Chapter 8 is about, okay, now we understand the time characteristics, temporal characteristics of the random processes from chapter 6. الautocorrelation function, cross correlation function, كل الكلام هذا. والtime average والpower and so on. كل ال statistical and time properties of the signal in chapter 6. And then we took in chapter 7 the spectral characteristics. We connected the autocorrelation function with the power spectral density, and we said that the power spectral density, it's a density function. It gives you how is the average power distributed among the different frequency components of the signal. Now in this chapter, we look at the response of linear systems when you have random inputs. So x of t here is a random process. And we have certain LTI system. This is the impulse response. H of t. So this is an LTI system. Linear time invariant. تذكر is linear time invariant. يا شباب. Linear means that if you have two signals added at the input, الoutput يكون the response of each signal alone added together. So this is the linear part. Time invariant, what does it mean? What does time invariant mean? If you
not function of time.
Exactly. If you excite the signal, if you work on the system now and you do it after 2 hours, the same input-output relationship holds. So the relationship between the input and the output is not a function of time, doesn't change with time. Time invariant. Tamam? So we have a system that is linear and time invariant. And we know from 207 that the input-output relationship between output and the input basically will look like y of t that looks like the convolution of x of t with h of t. لو تتذكر. صح ولا لا؟ This is in the time domain, and in the frequency domain you will see that y of f is equal to x of t multiplied by capital H of t, which is a transfer function. So what we'll do today is, or today and next class probably, we'll review the convolution equation, اللي هي ال LTI system impulse response equation, and then we'll talk about the mean and the mean squared value of the system response, the autocorrelation function of the response, the cross correlation function of the input and the output, and we'll talk about how can we evaluate certain impulse response using some random noise, and then we'll talk about the spectral characteristics of the system response, and then talk about cross power density function of the input and the output. So basically, the chapter looks like two things mainly: the autocorrelation function of this of the response of the system, and the cross correlation between the input and the output, the power spectral density of the response, the output, and the cross power spectral density between the input and the output mainly. So this is now, if I have a linear LTI, basically linear time invariant system with input x of t, output y of t. Then basically, considering linear and stable and time invariant system, the output is the convolution of the input and the some impulse response. You can have the convolution like this or like this, doesn't matter. It's only a change of variable. So now if I have a random output, so the random input, then the random output will look like, again, a convolution. Okay? Now let's see what happens to the mean and the power. Assuming White's station. We will assume White's station throughout this chapter. So basically the autocorrelation function is not a function of time. It does not change with time. The average is fixed. It doesn't change with time. And let's talk about the mean. The mean of the output of y of t, the output. It's expected value of y of t, right? Which is you take whatever y of t, place it inside the expectation. Okay? So it's expected value of the convolution between x of t and the impulse response. Now, usually we talk about expectation operator as a linear operator. Linear operator means it's a summation. Expectation is nothing but a summation or integration, صح? And assuming that both expectation and this integral inside it are convergent, so basically they don't blow off. You don't have an infinity in any one of them, which is the case in physical systems. You cannot have an average of infinity. Then you can exchange integration and expectation. Now exchanging means that I can insert the expectation inside the integral and only to the random thing only. So anything constant gets out of it. And anything random stays inside it. However, I know that it's a White-Sense stationary. So expected value of x of t minus lambda is nothing but x bar, right? So x bar is a constant, so you can take it outside the integral. And hence you have the mean is x bar, which is the mean of the signal, multiplied by the area under the curve of the impulse response, which is some y bar, which is a constant. So this doesn't change with time. So if I have a White-Sense stationary, the output White-Sense stationary input, sorry, of an LTI system, the output mean will be constant. It doesn't change with time. This is the first result. واضح شباب؟
ايوه واضح.
واضح دكتور.
ممتاز. يعطيكم العافية. Now let's look at the mean squared value. The expected value of y square of t, which is the average power of the output signal. Let's try to relate it with the average power of the input signal. Let's see. So again, it's expected value. So we take whatever inside here. We have y of t multiplied by, sorry. Okay, y of t multiplied by y of t. So we have double integral here. So we can combine the two integrals. Of course, every integral will have for delta d, sorry, d lambda 1, the second integral, d lambda 2. So we have two variables here. So you can combine them and exchange the expectation such that the expectation comes inside the integral and only for the random part. So anything that is not random outside the expectation. Impulse response is not random. So here we have expected value of x of t minus lambda 1 multiplied by x of t lambda 2. So if we look at tau here, it's t minus lambda 1 minus t minus lambda 2, which is the time difference between the first part and the second, time interval, time instance at which we are comparing the signal with at t minus lambda 1 minus the second time interval, instance at which you are comparing x of t. So basically it's t minus lambda 1 minus t plus lambda 2. So t cancels t. We have here lambda 2 minus lambda 1. which is similar to lambda 1 minus lambda 2 because نفس الشيء because r xx of tau equals r xx of minus tau. It's an even function, matter of fact. And because of that, we end up with expected value of x of t minus lambda 1, x of t minus lambda 2 as the autocorrelation function of lambda 1 minus lambda 2, or lambda 2 minus lambda 1, matter of fact. It doesn't matter. Same. Multiplied by the two impulse responses. So the power at the output equals the autocorrelation function multiplied by lambda h of lambda 1, h of lambda 2 integrated over the two lambdas, lambda 1 and lambda 2. This is it. So depending on how complicated your impulse responses, your impulse response, and how complicated the autocorrelation function, you will end up with probably complex or difficult integral to do. However, this is it. This is the mathematical result. Okay, Shba? Any question? Now let's have the white noise, our nice noise. White noise طبعا له ميزة كبيرة الوايت noise. Except طبعا in addition to being practically seen in band limited signals or systems, احنا قلنا انه it's wide, it's unrealizable. However, because it's very wide band, it looks like white for any system of operation that we work with. So the white noise, the autocorrelation function looks like an impulse. نتذكر n not over 2 multiplied by an impulse. هذه r xx of tau. It's an impulse with n not over 2. نتذكر. And this gives you basically the white noise, which is, if you take the Fourier transform of that, you will end up with the constant. This is the white noise. So now if we take this and we try to find the power at the output, then simply we just apply whatever we have done. It's the double integral of the autocorrelation function multiplied by h1 of lambda 1, so the h of lambda 1, h of lambda 2, d lambda 1, d lambda 2. Now we know if we integrate a delta with a function using the shifting property, we get the same function evaluated at the lambda. So here we get h of lambda, so the h of lambda 2, because this is shifted at lambda 2. So basically, using the shifting property, this becomes lambda 2. And hence we have, and the delta disappears. So we have the constant multiplied by h of lambda 2 multiplied by h of lambda 2 again. So h of lambda 2 squared, d lambda 2. So the output power will be equal to the input power, which is n naught over 2, multiplied by the area under the curve of the square of the impulse response. So this is equal to input power multiplied by product multiplied by area under h squared of t h squared the impulse response squared multiplied by بس عشان ما تخلطوها مع x, which is a signal probably or whatever. طيب واضح شباب؟ So the output power will be the input power multiplied by the area under the curve. The area under the curve of the impulse response square. Any question? Now similarly, we can find the autocorrelation function of the output. Again, assuming right sensation. So the autocorrelation function of the output is the expected value of the output multiplied by the output delayed by tau. Now, if we do this, if we do repeat the same exercise, but here instead of multiplying y of t by y of t, so we have here x of t minus lambda 1 و x of t minus lambda 2, هيكون في الثانية هذه هيكون instead of t هيكون في عندك tau so the t plus tau minus lambda 2 for the autocorrelation function, because we are multiplying expected value of y of t plus tau. So the second x here will have t plus tau minus lambda 2. And because of that, if you look at what we have here, we have a tau. So instead of having lambda tau, sorry, rxx of lambda 1 minus lambda 2, we'll have rxx of tau plus lambda 1 minus lambda 2. Which is a double convolution. So as if you are convolving rxx of tau once with h of minus tau, once with h of tau. Two-fold convolution. Okay يا شباب.
اوكي دكتور.
Any question? أي سؤال؟ طيب, this slide is a little bit busy, so we'll delay it until next time. أي سؤال يا شباب؟ Any question? Okay. طيب, I think that's enough for today. Next time, inshallah, we'll continue with the rest of chapter 8. Probably not complete, and we might end up with several slides. That will end, inshallah, on Tuesday. طيب, I am done يا شباب. اللي عنده سؤال I am here. أي سؤال؟
خلاص ممكن نطلع يا دكتور.
إيه, إذا ما عندكم أي سؤال go ahead. كلام. Time is up.
يا دكتور.
نراك على خير ان شاء الله.
حياك الله.
Have a nice weekend.
Have a nice weekend too. Thank you.